You all see my screen? The person swinging the ball around? Okay. I'm just going to close the door and I'll be back with you. All right. Oh. So, Ryan, no. Are you just running through here? Close the door. Take Murray with you. So asking you to define acceleration, I'm not going to have anybody define acceleration, but I just want you to think of that because it might help you a little bit to answer these other questions. And I think in at least, I don't know, the classes are all mixed up, but I know this has come up before. So this unit is going to start, this new unit is going to start with uniform circular motion, which means objects moving in a circle at a constant speed. And in this example, we've got a ball that's going in a circle at a constant speed. And the question is, what is the direction of the ball's acceleration? So I haven't asked you, is the ball accelerating? It is accelerating. I'm just going to tell you that. But now I want to know the direction. Does anybody know in what direction is the ball accelerating? I'm going to switch to another picture, and maybe you'll have an answer.
Is it accelerating outward?
That's a good guess. No, but you're on the right track. And I think I know why you said that, and it's good. That's a good instinct. So if this is this is a bad circle. Well, let's just say this is an actual circle, and the ball is going this way. 10 meters per second is its speed there. I'm not going to say S because S stands for other things. V is just going to have to stand for speed, even though it's really velocity. All right, so it's going this way right now. In a little while, it's going to be over here, and then it'll be going this way. And then a little later, it's going to be over here. It's be going that way. And then a little later, it's going to be here, and it'll be going this way. Does that give anybody any ideas? So the acceleration is change in velocity over change in time. So one way for velocity to change is for speed to change, but in this case, it's just, well, it's complicated, but just think of it as direction that's changing. So it was 10 meters per second to our left, and now the velocity is, or the speed, the velocity would be 10 meters per second downward on the picture, and now the velocity is 10 meters per second to the right in the picture. So
is it angular? Is the direction like angular?
But
like circular?
Pick a direction. And that's kind of tricky because the direction is different everywhere, but when it's right here, the change in its velocity is in which direction? Or in other words, if you were going to cause it to change its velocity in the same way that the string is doing, which way would you have to push this to make it move in a circle? Like, there's not a push. In this case, there's a pull, and I think that's kind of what Thomas was thinking about. Which way is the string pulling this ball in this position? Pulling it up, down, left, or right? Well, if you've got a string, the only thing that tension can do is really pull like that. And if somebody's holding it at this end, this is the person at the other end, then the person at the other end, they're going to feel the same tension going out. So this is really the only force that is acting on this ball. We could say, let's just imagine this is happening out in space to keep it really simple. This is the only force that's acting on it. This is the force that's giving it its net force, and therefore this is the direction that it's going to accelerate. So if you think of this as a car, if you're driving a car along and we're looking down on you from above, and you're going to our left, to you it feels like you're making a left turn. You're going like this, you're turning left, turning left, turning left, turning left, turning. So this would be a constant left turn, and a left turn is toward the center. So the quick answer to this is the acceleration is always toward the center. When the ball is over here, it's accelerating this way. When the ball is down here, it's accelerating that way. It's taking its current direction, and this represents the change in the direction. The online textbook, which I'll show you briefly in just a minute, does kind of a cool thing. It uses vector addition to explain how the change in direction and therefore the acceleration is toward the center. So it says, imagine this velocity vector, and I think they call it v1, and then imagine this velocity vector, and they call that one v2, and they say, what sort of a change do we have to cause in this to give us that? So it's like, we've got this vector, we want to add something to this to get that. So this is a component, this is a resultant, and they create a little head to tail diagram where this is a vector v1 that they connect tail to tail with with v2. This is a component, this is the resultant, and then they ask, what other kind of a third vector do we need to add to this to get this new velocity? And the answer is this, and they call this delta v. So this represents the velocity right here. This represents the new velocity down there. And this represents the change in velocity that we have to add to our current velocity to get the new velocity. And if you look at the direction of this, it's pointing right in the center of the circle. I'm just going to go to this online textbook for a couple of reasons. One is, I never do. I just want to remind you it's there. And the other is, I want to point out something that if you decide you want to, oh come on, I swear I just clicked that. If you decide that you want to go over the derivation of this formula I'm going to share with you, I want to warn you about something. Those called OpenStax. This is the chapter on centripetal acceleration. Centripetal means toward the center. So when you're swinging something around on a string, it feels like it's pulling straight out. It's not actually. What it's trying to do is it has momentum or inertia that this ball is being carried in a path that's tangent to the circle. And you have to apply what's called a centripetal force to keep it from going straight. So that centripetal force is what causes it to turn in. There really is there's no force this way. It feels like there's a force that way. It feels like if you broke the string, this would fly straight out, but it doesn't. It's inertia just carries it that way. So there's no such thing as a centrifugal force, which means outward. But let me go back to the textbook. Cancel. So if you read this page and you want to go through how they arrive at this formula, which is right down here, centripetal accelerations v squared over r, they make the statement somewhere in here that says these two triangles are similar. It says, note that the triangle formed by the velocity vectors and the one formed by the radii are similar. So that threw me when I was reading this. Here's what they mean by this. I'm not going to show you why they're similar. I'm just going to explain to you what they're talking about. And I apologize if I mess up my... Ooh. writing. I don't know why this defaults to such a large pen. So they've drawn a diagram pretty much like I just drew, except this velocity and this velocity. I drew my V1 here, and I drew my V2 down there, and then I added them together. Let me erase. So they've taken this second velocity and this first velocity, and they've put them together up here just like I did. So here's the first velocity, here's the change in velocity, and this is the new velocity that you get when you add the current velocity and the change in velocity to get the new velocity. Now, the similar triangles they're talking about are, well, this angle is theta, and this angle is theta. So this triangle right here is similar to this triangle right there. And you can show that it's similar, but I'll just point out that it turns out this is theta, and V1 and V2 are the same, because in uniform circular motion, speed isn't changing. Just like R and R, these two radii are the same, because the radius of a circle is the same everywhere. So you've got basically two isosceles triangles with the same angle theta, so they're similar. So if you want to go through this, the derivation on the page, feel free to do that. I had thought maybe I would go through that because this is such a central formula to what we're going to be doing, but I'm not going to. I'm just going to suffice it to say that here's the formula. I'll talk a little bit about it, but I'm not going to derive it for you. So let me ask you the other two questions, which are, I should have just gone back. I can do that. How's the ball's acceleration related to its speed, and how's the ball's acceleration related to the length of the string? So go into my picture for that. And I'm going to write the formula that I just showed you that they derived in the textbook. So it's called centripetal acceleration, and it is acceleration whenever something's moving in a circle at a constant speed. And it's equal to v squared over r. So if you have a ball or something on a string, or it could just be a planet orbiting or whatever, and it's going in a circular path like that, and the radius is this distance, and the velocity is that. My first warm-up question is, what happens to the acceleration if you speed this up? So if this goes from 10 meters per second to 20 meters per second, you're swinging the ball around faster, and the answer is the acceleration goes way up. And you feel this, you feel it not only because the acceleration goes up, but because net force equals ma, and this A is that A, and you have to, if you're swinging the ball, you have to apply a force to make it do this. You're going to feel the force increase and increase and increase a lot as the ball goes faster. And then as the radius shrinks, like if you keep swinging it at the same speed and the ball moves in closer, I usually give the example of lifeguards. When I was a kid, I used to spend a lot of time at the swimming pool, and the lifeguards would swing their whistles around their fingers. They always had a whistle, and the whistle would go like this. It would go around and it would get closer and closer and closer and closer and closer and closer. And as it moves in, even if the speed of that whistle doesn't change, having done that before, do you feel more force or do you feel less force? How many people think you would feel less force as the radius moves in if you're swinging something in a circle? You keep the speed the same, but the circles are just smaller and smaller and smaller. Nobody? Because you would feel more force. So centripetal acceleration and centripetal force, which we'll be doing a lot with, are inversely proportional to radius. So if you want to turn a really tight corner in a car, you're going to have more, you're going to feel more G's, and you're going to need better tires than if you're going to turn a bigger circle, because you're going to have a bigger acceleration if you have a smaller radius. And if you go around a corner faster, then you're also going to need better tires so that you don't skid out. Right. That's I feel like I've beaten the proverbial dead horse with that warm-up. Now, today, if anybody wants to go over any of the homework questions about the 2D Newton's Laws problems, either the optional ones that I assigned yesterday or the ones before that, happy to go over that. We can talk about the test, which people are going to have on Friday, Gold Group. But we can also talk about that test tomorrow. So does anybody have any questions about the Newton's Laws stuff? Basically 4 kinds of problems that you're going to have to do. All right, well, let me quickly just, since nobody has any questions, let me just kind of talk about, really briefly about the test on Friday. So I won't go to that. This class 3 practice that I'm opening up now, this is probably the closest thing to what the test is going to be like, with one exception. So the one exception on Friday, the thing that'll be a bit different from this, is that these 2 angles are going to be different. So having the angles the same in some ways make things easier, but I think it just makes things trickier too for people. So these will be 2 different angles. You're going to have to find tension in the 2 strings. There's going to be one like that. All I'm going to be able to change in this problem is the angles and the mass. But aside from that, it's going to be the same scenario. And then Claire, Blue is going to do it on Monday. Blue and Remote on Monday. So for number 2, there's going to be an incline like this. I might have the incline tilted to the left instead of tilted to the right, so it would look like, I'm going to use this pen, maybe it works this time. Why is it always so big when I start? Anyway, it could be like that instead of like like this. Ms. Royer shared this epic pen with me. I don't like it so far. This, sometimes this whole thing, I'm going to try to shrink the pen size down. Sometimes this whole thing is going to accelerate this way, and sometimes it's going to accelerate that way. I can vary this mass. I can vary the coefficient of friction. I can vary the angle. I can vary that mass and make different things happen, but it's going to look just like this. Then on the third problem, there's really very little I can do here. I can make this thing, hey, it defaulted again. I can make this thing swing the other way, like this, and I can change this angle and I can change the mass. So that's all I can do to that one. And then for the one down at the bottom, come on. Doesn't let me move unless I erase. I don't know. For this one, I can change the mass. I can make it be pulled to the other side instead of being pulled to this side, so it could be going like this. This angle might be different, mu might be different, but it's basically going to be the same thing. So, does that jog any questions free from your minds? All right. Well, let's do.
Are you going to leave a table in, or are we just going to?
Yeah. There's going to be a table just like this. And I mean, if it's any different, I might ask for more things. Let's see. On this one, I asked for the box weight, the y component, the x component, the normal force. Yeah, that one, I wouldn't see needing to change anything. Let me look at this one up above. Whoop. I think this is all good. Yeah, on here, this one, I think this is good too. If I have two different angles, then clearly I'd have you calculate the weight of the hanging object. I don't know if I would even ask you for a vertical component of either tension. I would just ask you for the two tensions. So it'd be the weight and then the two tensions. Tension on the left string, tension on the right string. I might see if I can come up with some way to break the problem down, but this is one where you really don't have an answer until the end. So you'll have a bunch of steps in there. Just please show your work if you want partial credit. Other questions? All right. So, trying to find my way to my web page. The snow day caused me to change the class numbers, but I'm still going to try to finish everything up with Kepler's laws and gravitation and circular motion before break, so we're not having a test right after break. All right, so I just want to go over a couple of example problems, and then after that you have time for homework. So if you don't have the Unit 5 packet, I think I've got a link to it in Google Classroom. You can also, for now, just work on a sheet of paper, follow along however you want to, and I'm going to do a couple of examples. The formulas are up at the top. We really don't have any notes here. If there were any notes, it would be a derivation of this, of centripetal force. But if you want to see that, you can just look in the textbook. So essentially, anytime something is traveling in a circle at a constant speed, this is its acceleration. And I kind of like, I'm going to rewrite this. I'm going to write F centripetal equals mv squared over r, and then equals net force for centripetal motion. I get hung up over the exact way that I want to label these things, but basically the F equals ma, that's still true. Newton's second law is not going to be untrue anymore, but in the particular case when something's going in a circle, we know that the acceleration is this, so you can substitute v squared over r for a, and that gives us mv squared over r. Actually, I guess this is okay. I don't know. I guess I'll go with that. So that is the net force when something's in centripetal motion. We're going to be doing basically the same thing we've done all along, except instead of F equals ma, we'll have F equals mv squared over r. So here's a problem with a 500 kilogram car traveling in a circle with a radius of 20 meters. If the car maintains a speed of 20 meters per second, what centripetal force acts on the car? And then if the driving surface is flat and horizontal, what provides the centripetal force? So I'm just going to draw the car right here. And the car is going to be going to our left. It could be going any direction, but I'm just choosing that it's going to our left. And it's traveling in a circle like this, and there's the center of the circle. So this is a 500 kilogram car, and its velocity is 20 meters per second, or it's 20 meters per second to the left. And I want to draw all the forces acting on it, and I want to add those up to get the net force, and then I want to use F equals ma to get the net force. So where I'm going over here is just like always. This is F equals ma, except instead of F equals ma, it's now F equals mv squared over r. So I'm going to calculate the net force that way, and then I'm going to calculate the net force as the sum of the forces acting on the car, and then I'm going to set them equal. So if this car is going in a circle at a constant 20 meters per second, what are some forces acting on the car? My dog is whining. I'm going to let her out. Think about that. I want to know one force acting on the car. Susie, come. Go. All right. Anybody? And I should say this, we're looking down on the top. This is the top view of the car now. It's not a side view. If we were looking at the car from the side, this is the car on the ground. We would draw weight. Nobody's said weight yet. But if it's on level ground, it's not going up and it's not going down, that means there's the normal force, which is the same as weight. So these are canceling out. So in my drawing, I'm not going to draw those because they're not really doing anything. The car's not accelerating up or down. It is accelerating toward the center. It's accelerating directly this way. That's the centripetal acceleration. I'll just write AC right there. So there's got to be a force pushing it toward the center. What is the force? What's pushing it? How does a car turn? It's got to, if you're driving down the road and you want to turn left, something's got to push you to the left. You can't push yourself. What's pushing the car? Oh wait, is that a hand? Or is that just an old hand?
Yeah.
Oh, Claire, what's pushing the car?
The ground.
The ground, yeah. And now if this were super slippery ground, could the car turn? It couldn't. It would just slide. It wouldn't go in a circle. So you could either call this the, I'm just going to draw another arrow here. You could either call this friction or you could call it the ground. I'll just say the force of the road. So basically the road is pushing the car to the left the entire time. The car is pushing the road the other way, but we're only including forces that are acting on the car. And that's it. Let's not get into drag or anything here. We're back to things taking place in a vacuum because it's simpler. So there's really only one force. That would be the force of the road. All right. So the net force acting on the car is mv squared over r. The individual forces, there's only one, and that's the force of the road. And now the way I've got them drawn here in my diagram, it kind of looks like they're going down. So I don't know, I'm torn about what to do. But since the net force is going to be always toward the center with uniform circular motion, and since I've drawn it this way, I kind of want to say this is negative mv squared over r, since it's down. And then the force of the road would be a negative force since it's also down. I'm just going to leave them for now. I'm just going to leave them like they are. And I'm going to write mv squared over r equals the force of the road. So what centripetal force acts on the car? That's not really asking me any deep questions. That's just asking me to calculate this. And when I calculate this, that's also going to give me the road force. So I will have answered the second part. If the driving surface is flat and horizontal, what provides a centripetal force? So let me just plug and chug at this point. The mass of the car is 500 kilograms. And the velocity of the car is 20 meters per second. And the radius of the circle is 20 meters. And that equals the force of the road. So 20 divided by 20, this is 20 squared divided by 20, so one of those 20s is going to cancel out. So this is just 500 times 20, which is 10,000. 10,000 newtons equals force of the road. And I'm also going to write equals centripetal force, which is, I guess, another name for, it's another name for a force that's pointing toward the center of the circle. So I said a lot more in doing this problem than I really needed. All I really needed to do was that, and then in the end say, where's this force coming from that's pushing the car toward the center? Well, and the answer is the road. So in the next problem, in this one, I'm actually going to need to do this kind of thing. It didn't hurt here, but it wasn't really necessary. So this is an example of a horizontal circle. When you are doing these problems, you'll see some say horizontal, some say vertical. In physics teacher speak, horizontal circle means we're looking down on this circle from above. This is all taking place on flat ground. The whole circle is in the horizontal plane. Now a vertical circle would be, you flip it up, the circle is in a vertical plane, or the axis is horizontal. So this would be like, for example, a Ferris wheel. And that's what's going on in this problem. So the problem is going to be figuring out what force is acting on some person when she's at the top of the circle and what force is acting on the person at the bottom of the circle. And here we go. So a 60-kilogram teenager is at the county fair. Currently she's on a circular ride that revolves its passengers in a vertical circle. So you go up, you go down, you go up again with a 4-meter radius. Her speed is kept constant at 7 meters per second. As she revolves, she's supported by a cushioned pad. Inside the pad is a scale that records the normal force exerted on the girl. I don't know why I didn't say she's just standing on a scale, like an elevator problem, because that's how I'm going to draw it. I'm going to draw her standing on a scale inside an elevator, except it's not going to be an elevator. It's going to be more of a Ferris wheel. So that's the top, and this is going to be the bottom, and it can be going any direction. It doesn't really matter as long as we're going in an exact circle at a constant speed. And when she's at the top, she's standing on this scale, and when she's at the bottom, she's standing on this scale. And the question is about the normal force, but basically it's what is the scale going to read when she's at the top, and then what's the scale going to read when she's at the bottom. Where do you think it would be? How many of you think she's going to have a heavier reading on the scale when she's at the bottom? Raise your real hand or your fake hand or any hand. If you think the scale's going to say she weighs more when she gets to the bottom. How many people agree with that? Okay, so almost half, and maybe some unresponsive. She is going to feel heavier. Sorry, I'm eating and talking. And if you've ever been on a fast ride like this, or a roller coaster, when you go through dips, you start to feel really heavy. And then when you get to the top, at the right kind of speed, you might even be weightless. Or if this is fast enough, she might even start to levitate at the top. Like you go over a hill on a roller coaster fast enough, you're going to fly out of the seat unless there's some bar holding you in. And I don't know why I hadn't changed this in the past, but we discovered last class that based on the information, that's what happens here. So let's slow her down a little bit. Let's keep her speed at a much safer 5 meters per second. Because if we don't, she's going to fly off and we're going to get some sort of negative normal force, which is just weird. I checked several times to make sure that our calculations were right last class, and yes, there was a negative normal force. So first I'm going to do the top. So just like all the other problems we've been doing for a long time, I'm going to write the net force equals ma, except in this case it's not going to be ma, it's going to be mv squared over r. And the tricky thing about this is you can't just write mv squared over r. You have to think about the direction. At the top, the net force is toward the center, so the net force is going to be down. And at the bottom, the net force is toward the center, because that's just the way the acceleration is in uniform circular motion. So the net force is toward the center and it's up, which means it's going to be positive. So when she's up here, she's going to have a negative net force acting on her. When she's down here, she's going to have a positive net force acting on her. So at the top, because she's in a circle, her net force is mv squared over r. Because that's directed toward the center and the center is down, it's negative. So that's her net force. The other way to get the net force is to add up all the individual forces acting on her. And this is going to seem pretty familiar. If you think about the forces that are acting on her, you should be able to tell me the two. There's weight, and then there's the normal force. So gravity is pulling her downward, that's her weight. The normal force, the surface right here, is pushing her up. And that's really it. Those are the only two forces acting on her that aren't canceling in some way. And her weight, I'll just go ahead and write that. 60 times 9.8 is 588. And the normal force is not necessarily equal to her weight in this case. Normal force and weight are the same when something's just sitting on the ground, when there's no acceleration. But she's not just sitting on the ground. So I'm going to write the net force as the sum of the forces. It's the normal force minus her weight. And now I'm going to set things equal. So this is one way to write her net force, and this is the other way to write her net force. When I bring these together, I'll plug some stuff in. So her mass is 60, and her velocity is 5, and the radius of this thing is 4 meters. So that's negative mv squared over r, which is her net force, and that's equal to the normal force minus 588. And I don't know what net force I'm going to get, but I know it's enough that she doesn't fly up into the air. So 25 times 60 divided by 4 equals 375. So the net force acting on her is negative 375 newtons. So that's the overall force that's pushing or pulling her downward, that's keeping her following this trajectory. She's going to the left right now. That's the downward net force that's causing her to curve downward. And that equals the normal force minus 588. So if I add 588 to both sides, I get 213. So that's how heavy she's going to feel. Normally she's a 588 Newton person, but the scale is only going to push up against her and read 213 newtons when she's at the top. So she won't feel totally weightless, but she's going to feel a lot lighter. And then at the bottom, I'm going to do everything again, and it's really all going to be the same, except the direction of the net force is now upward, because it's toward the center of the circle, and the center of the circle is above. So the net force now is not negative mv squared over r, it's mv squared over r. And I'm just going to write, what is that, 375 newtons, because I've already done that. And then the net force, being the sum of the forces, the two forces acting on her are her weight, which is 588, and the normal force of the scale, which is pushing up. So it's going to be the normal force minus 588. So this equals that. So now I add 588 to both sides, and I get 963 for the normal force. So that's not quite twice her weight, but it's quite a bit more. If she ordinarily feels like she's 588 newtons, in this circumstance she's going to feel not quite twice as heavy, but almost twice as heavy. And the faster this goes, I mean, if you, instead of, if we turned her upside down up at the top and had her in some cage where she was like this, you could spin her really fast then. You could have her swing down and get super heavy here, and then she'd be going so fast there that her momentum would push her up against the scale and she wouldn't fall off even going upside down. So the practice problems on here, I got rid of number 2 in Google Classroom. Number 1, this is really just using mv squared over r. Number 3, you have to, this is the bathroom scale inside a Ferris wheel kind of thing, so you have to apply some of the other trickier things that I did. But that's it. If anybody wants to stay and ask me questions, I'm happy to hang out and talk to you, but otherwise you can go and get this